Hey, Dr. Clark, coming back at you with another example video, still in section 7.5 on impulse forcing in the Dirac delta. Let's take a look. So this looks like example 2. We've got an undamped oscillator beginning at rest and then tapped. Okay, so this is interesting because what they're saying here is we're starting with initial position of 0 and initial velocity of 0. So actually, if you started with initial position 0 and initial velocity of 0, you would just persist at 0. The solution would be y of t equals the 0 function, right? That would be the answer to any differential equation or any second order differential equation. Any homogeneous second order differential equation with initial conditions of 0 and 0. What's going on here, though, is they're saying, no, you've actually tapped it with a hammer at time equal to 0. So they're sort of pretending that it was at rest and then it was impulsed with a hammer to get it going. And that's going to be kind of an interesting little idea here. So they're giving us the Dirac. You might write this as Dirac t minus 0 if you wanted to. Okay, so let's run this through the Laplace transform to try to solve it. If you do, you're going to get what? SL of y prime minus y prime of 0 plus 2L of y equals 3 e to the minus s times 0, right? So that is, because it's e to the minus s t naught would be the Laplace transform of the delta at t naught. So if t naught is 0, it's just e to the minus s times 0. Okay, but that's really just going to be e to the 0, which is 1. So you're just going to get 3 on the right-hand side. Okay, and now in this case, we're going to have to continue on the left-hand side. So we'll have S, and then we'll have SL of y minus y of 0. Y prime of 0 is 0, and so then we get 2L of y. And then let's see. So y prime of 0 was 0, y of 0 was 0. So those both cancel out, and so you just get s squared plus 2 L of y equals 3. So L of y would equal 3 over s squared plus 2. If I just take the s squared plus 2, divide it to the right-hand side. Okay, so that's interesting when you take the Laplace transform of the Dirac delta where t naught is 0, you just get sort of just a number 3 in this case. And so then all we have to do to solve it is just inverse Laplace transform that. And that's going to be what? It looks to me like a sine function, but it's not quite set up right. So let's see if we can rewrite this as 3, and then I would have 1 over s squared plus 2, but that's not quite right because 2 is not a perfect square. Well, it is. It's really root 2 squared. That's what 2 is. And so then I need root 2 in the numerator so that it matches, but I'll have to divide by root 2. So that, you can't just write root 2 in the middle of nowhere for no reason. So, okay, if I write root 2 over root 2, that didn't change it. I factored out the 3. And now I've got it looking exactly like sine function, right? So I'm going to get 3 over root 2 times the sine function of root 2t, okay? And that is the solution right there. Okay, so it's basically sine function. Of course, if you go back to the original differential equation, it was undamped. So we should have expected sine or cosine. The characteristic equation was s squared plus 2, so sine of root 2t makes sense. And then that 3, that just kind of said that. Now, what you should notice is if I plug in y of 0, I do get 0 because sine of 0 is 0. Y prime of 0 is going to be 3 over root 2 times root 2 cosine of root 2 times 0 if you take the derivative and plug in 0. But that will, of course, equal 3, which was what it's sort of like the initial position or the initial velocity is 3, but I thought the initial velocity was 0. Well, it was and it wasn't because we tapped it with the hammer at t equals 0. So essentially what you might notice from this, and I think I even put this in as a question, is solving this differential equation any different from solving one with no forcing term, but then initial velocity is 3, and the answer is no. They're the exact same thing. So you can set initial velocity to be 0 and then tap it with a hammer at t equals 0, or you can just ignore the delta function, the Dirac, and then set the initial velocity to be 3, and you'll get the same answer. So that's kind of a cool little way that Dirac happens. Now, of course, when the t is not equal to 0, then your initial conditions are at t equals 0, and then the Dirac would happen at a later time. But in this problem, you can see that sort of that Dirac really just changes your velocity. That's really what it's doing. It's an instantaneous change in velocity. So hopefully that one was helpful, kind of changing it up a little bit and thinking about how the initial conditions play around with Dirac functions. We've got one more example coming in the next video, so take a look at that one as well.